All right. So welcome back to this YouTube channel. So yeah, in the last video we have looked at a specific type of generative adversarial network called cycle GAN, so in which we could actually do image to image translation. Given an image, uh, predict other image belong to a completely other distribution, and some type of unsupervised learning problem. It is an unsupervised learning problem. So in this video, we are going to look at other type of GAN. Here, not image to image translation. Here, we are not going to build image to image translation, but just a little better model, a better generated adversarial network than the normal GAN. So we'll be training essentially new idea, not a new architecture. We are not going to discuss a new architecture, but just a new idea of training, like how we can train this models and all that. So this is the paper. Progressive growing of GANs for improved quality, stability, and variation. Right. Okay. So the name of the model is ProGAN. It is actually called as ProGAN. So the main idea is actually progressively build up layers. So we are going to go through this paper in this video. I think, yeah, I mean, we'll just go through this paper in this video, and in the next video we'll try to code it in TensorFlow. We'll try to program this generative adversarial network or GAN. So first, as you can see here, I'll just show you some results of this paper just to make sure just to give you a base context on what we are solving. So all the images that you see here are generated by GAN. Of course, they are not like up to the mark, but this paper was released in 2018, or I think, sorry. So probably released in 2018. So, but still the images were pretty good. The as if you can think about it, the paper is pretty old compared to this compared to 2023 and all that, but still the performance is actually pretty good. You can see yeah, you can see some really good human images, right? So like based on different contexts and all that. So that is the results, right? We could actually add conditional GAN if you want to. You could add a condition, maybe generate according to a specific class or something. You could add that. But here we are just doing like normal image generation. You just give an image and just predict an image. That is what we'll be doing. So the basic idea, so if you can read about it, we describe a new training methodology for a generative adversarial network. So basically, the paper is not actually providing us with a completely new architecture or completely new idea, other than generative adversarial network. But what the paper is going to give us is just a new training methodology, just a new training method for us to train our model, right? We could just train these adversarial networks. I mean, they have proved to be pretty good, right? So as you can, if you just read it, the key idea is to grow both the generator and discriminator progressively grow both the discriminator and the generator. Starting from a low resolution, we add new layers that model increasingly fine details as training process. Right, this both speeds the training up and greatly stabilizes it, allowing us to produce more images of unprecedented quality. Example, Celebia images at 1024 square. We also propose a simple way to increase the variation in generative images and achieve a record inception score of 8.80 in unsupervised Cipher 10 dataset. Additionally, we describe several implementation details that are important for discouraging unhealthy competition between generator and the discriminator. Finally, we suggest a new metric for evaluating grand results, both in terms of image quality and variation. As an additional contribution, we construct a high quality version of Celeb dataset. These are like the basic abstract of this data of this paper, like basic thing. Here we like some papers are like made some type of shout out here to GANs and VAEs and all that, right? Pixel CNNs. Yeah, you could see some like known names here. I'll try to cover VAE, variation autoencoders, in the future videos. So I mean, yeah, he could read all that, Git critic and all that. So the basic idea is progressively growing of GANs. Like I'm going to tell you the basic idea. I'm going to go to the whiteboard. So the basic idea is, let's say given some training images, given many training images, So the idea is take these training images. What is happening? Like take these training images. These circles represent images, by the way. So the basic idea is just take these training images as training, and when you are generating it, like you like when you are building the generator, right? You have the CNN model, let's say with different kernels. So each circle represents a kernel, let's say. So we're gonna have many kernels. So top to bottom, I'm drawing like that. So yeah, I mean you understand, right? Well, now not going to draw this. Just makes the diagram more messy. So we're going to pass that to a CNN to generate an image, like based on these images, and we're going to pass that through a discriminator, right, which is going to predict how good that image is, right? And then we're going to compare this like based on that, right? You understand, right? That is the idea of a generator. This is a generator. So what we are going to do is, rather than predicting a like very high quality image, we are going to start off like while training. I'm going to like progressive GANs is only this idea is actually only used while training, because of course why do we want to predict low quality images while inference time? So first we'll start off by predicting, let's say 4 into 4 pixels, right? Yeah, yeah, we're going to generate, like, first of all, while training we'll start off by predicting or drawing or generating 4 by 4 images, like very low dimensional images. And as we go on through training, we are going to use a very like pretty good intuitive engineering. We're going to have we are going to look at that in just a minute, or within just some few minutes. So we're going to slowly transition the model and slowly add more layers and and slowly add like higher amount of pixels as the output. So when starting off, I'm just going to draw the CNN of generator here. So let's say we can have like 4 by 4 convolution, right? 4 by 4 kernel CNN, and then we're going to have yeah. So while starting off, let's say in the first epoch we're going to have 4 by 4 CNN, and we're going to generate an image, and then the discriminator also is going to have a 4 by 4 CNN, right? It is no the discriminator is going to take this 4 by 4 CNN and generate an output. And as we go on, as we move on with training, we're going to increase the size, we're going to increase the number of CNNs, we're going to add another CNN another CNN transpose layer, and we'll just increase this size. So as we add more CNN transpose layers, we are going to increase the size, and thus the discriminator and the discriminators like the discriminator's architecture is also going to change. We are going to add more CNN layers to discriminator and more CNN transpose layers to the generator, hence making the image more bigger and more like with higher quality and clarity, right? Or with more complex images. We'll generate more complex images. I think that's a very good word. So we'll keep on adding more and more CNN transpose layers, CNN layers or CNN transpose layers. And we're gonna have more and more CNN transpose layers in generator and more CNN layers in discriminator based on the number of like layers, CNN layers in this GANs in the generator. So that is the basic idea. So therefore we'll keep on increasing complexity, keep on increasing, like start off very slow, like start off with like generating very small images, very low quality images. 4 by 4 pixels is like uh, just very low quality image. You will not understand it. Like there is no patterns in that 4 by 4 images. Like just it just predicts some type of patches, just some type of data, and then it will pass to discriminator. And slowly as we go on, we'll just keep on updating this CNN layer, CNN architecture. We are as we go on through training, we'll update the CNN architecture of GAN and the discriminator, sorry, generator and the discriminator, and then slowly we'll build up more complex images, more bigger images, and then that is how the training goes. Again, we're going to train the models in here, so you understand, right? So that is the idea. That is the idea of how we do this. And let's just go through this paper and maybe find about something. Again, you have this chat GPT, right? You have chat GPT. Just go on, just search for these GANs maybe. I mean, it will be very useful. Like I mean, if you want to read any research paper that is published before September 2021, you can just go to chat GPT and just read some, I think. So Yeah, that is the basic idea that is shown here. So first we are going to start off by, let's say, 4 by 4 CNN. So we're going to take latent dimension, latent as our as input, the latent noise as the input. And if the as we go as we like as you can see here, as the training progresses, we are going to add more and more CNN layers, CNN transpose layers in the generator, and more CNN layers to this discriminator. So as you can see here, first we'll have 4 by 4 CNN layers, like only one CNN layer with like 4 by 4 output, and then we're going to have we're going to increase the size to 8 by 8. So the generator will first produce a 4 by 4 and then 8 by 8, and then the discriminator is going to take this 8 by 8 image and generate a 4 by 4 output. So the discriminator is essentially going to take this image and then perform a 8 by 8 CNN, which is going to just decrease the size of this model. And like based on the discriminator's output, we'll update the GAN. So that is how it goes. And finally, after like a lot of epochs, as we move on with training, and after a lot of training steps, we'll finally achieve this 1024 by 1124 pixel images. So 10 10 10 24 images, like higher quality images. So that is the idea, right? So that is the idea here. And then there is also mini batch standard deviation. So essentially what we'll be doing is I'll just cover this first. So as you can see here, we are going to the method of like increasing the complexity, increasing the number of like increasing the dimension of this image, of the generated image, is actually pretty smooth. We want the transition from like 4 by 4 image to 8 by 8 image very slow. We want to add this like CNN layers very slowly. So that is why we have this very good architecture. I'll just go through and explain what is going to happen. So we're going to have, I'm going to copy the diagram here. I'm going to draw this diagram. I can copy it. I'll just draw this. I'll only draw the middle part. So what we're essentially going to do is we're going to have a like another CNN layer, maybe 32. Yeah, we're going to have another CNN layer, another CNN, and then we're going to have this model, and then we're going to add this to a function. Right. So the basic idea is we don't want to transition. We just don't want to add more layers just like that. So therefore, what we'll do is we'll after we have performed this CNN, after let's say we want to increase the amount of increase the amount of layers. So we'll have a constant called alpha, let's say. So we'll have a constant called alpha, and we'll actually change this alpha as we go on through training, as we move, like as we perform more training steps. So what we'll be doing is after we have performed this CNN, after the first CNN, like just taking the image and predicting a 16 by 16 vector, we're going to perform a CNN, right? And then we're going to get an output. And rather than just making this output as a final output, like adding more CNN will of course increase the performance by a lot, increase the uh, model performance by a lot, and we don't want that because it will undermine the stability of the model. We want to slowly transition, because like to make the trainable parameters more just for the simple sake that we want the trainable parameters to change slowly, and we don't want them to like move around the local minima, like just we want them to converge. So therefore we will take this change slowly. So what we'll do is, rather than just like for let's say this is A and this is B, maybe this output is A and this output is B. So rather than adding A plus B, what we'll do is we'll say A plus alpha into B. So this alpha will go from 0 to 1, right? As we get started, this alpha is going to be 0, right? As we go on, as we start with training, this is going to be 0, and then therefore this output will be given higher importance, and as we move on, this will become higher and higher, and thus this like the amount of interference and amount of and like this will be given more importance. This output will be given more importance, thus increasing the complexity. And in fact, like we'll have like I'm just going to In fact, right? So we're going to have many of these layers. We're going to have many of these layers. And then each will have its own alpha values. Right? Understand, right? So this will have its own alpha value. This will have its own alpha value. This will have its own alpha value. And as we want, we'll comparatively based on the like the number of layer, we'll update this alpha values as we go on. So thus, we will have these many of CNNs, and we'll slowly update this alpha value to actually increase the interference of this CNN in the output of this or generator output. So that is the idea of like slowly adding this change. And then normalization. GANs are prone to escalation of signal magnetic, right? Equalized learning rate. Yeah, I mean, like, so we will do something called pixel wise feature vector normalization. So essentially what we'll do is we'll just take every pixel and find the mean and standard deviation, right? And then like we'll just make sure the fixed pixels are normalized, right? I'm just going to read that. To dissolve the scenario where the magnitudes in the generator and discriminant spiral out of control as a result of competition, we normalize the feature vector in each pixel to unit length in the generator after each convolution layer. We do this using a variant of local response normalization configured as bxy is equal to axy in square root of 1 by n, like mean squared, like mean squared error, mean squared, yeah, plus epsilon, where epsilon is a very small number. And then we find it surprising that this heavy-handed constraint does not seem to harm the generator in any way. And indeed, with most dataset, it does not change the results much, but it prevents the escalation of signal magnitudes very effectively when needed. So therefore, to control the signal magnitudes, like we don't want the magnitude or the outputs to like go out of the range. So therefore, to control the escalation of like these magnitudes, we use this normalization technique, right? And then yeah, so we have a bunch of experiments, and yeah, these are the images that are formed, right, by different models, I believe. Yeah, so by different models and like by using different hyperparameters. So like Wasserstein GANs, like using Wasserstein laws and all that. So as you can see, A is nothing but using Wasserstein something. Yeah. Yeah, so these are the results. As you can see here, and like this is the paper overall overview. And I mean, this video I have only put this video as the, like introduction to this ProGAN. In the next video, even I will do some research, because like this is the first time for me actually reading this paper. This is the first time for me to actually read this paper, ProGAN. And maybe in and in the next video tomorrow, I'll read everything. I'll probably like I think I will try to implement it before you, or even I mean, like implementing before you in this video will be in a video will be very hard, because like number one, I have to train the model. If I have to train the model while recording this video, that might make my computer slow. And number two, it might take time. Like implementing will definitely take time. It will have we'll have a lot of errors and all that. So I'll try to implement this model maybe by looking at some of the previous implementations, or even like I mean, like I don't think there is a like huge changes that we should make. We should just like create some basic Python logic to actually create this architecture of increasing the number of layers. Or we could actually use this epsilon, like many alpha values, to control the. And I mean, I'll try to cover. I'll try to come with something in the next video. So this is this is just like an introduction to ProGAN. So I'll see you in the next video, where we'll actually learn more about ProGAN and actually build it in TensorFlow. So thank you for watching, and I'll see you in the next video.